We live in a universe so vast that scientists may never finish exploring it. However, as the curious beings we are, we wonder what is outside the universe and what goes on there. We may never be able to step out of our universe to observe what lies there. However, researchers have come up with ideas about what goes on outside the universe. In this video, we bring you 6 theories about what lies outside the observable universe. Number 1. Hubble volume. Our universe, like everything else in physics, tries to exist in the lowest possible energy state. However, inflationary cosmologists say that around 10 raised to the power of minus 36 seconds after the Big Bang, the universe found itself resting at what is called a false vacuum energy, which, confounding enough, is a low point that wasn't really a low point. So in its quest for the real nadir vacuum energy, the universe expanded by an astounding factor of 10 raised to the power of 50 in a fraction of a second. Our universe has not rested since then. It has continued to expand, but at a much slower rate. The light from distant objects is evidence of this expansion. The stretching of space causes photons emitted by a star or galaxy to lose energy as they travel across the universe. And when these photons reach us, their wavelengths have been redshifted in proportion to the distance traveled. This is why cosmologists describe redshift as a function of both space and time. The light from these distant objects has traveled so far that when we finally see them, we see the objects as they were billions of years ago. Redshifted light allows us to see objects such as galaxies as they existed in the distant past. But what it does not allow us to see is all of the events that occurred in our universe throughout its history. Because our universe is constantly in a state of expansion, some objects' light is simply too far away for us to see. The physics of that boundary are dependent in part on a region of surrounding space-time known as the Hubble volume. On Earth, the Hubble volume is defined by measuring the Hubble parameter, which is a value that relates the apparent recession speed of distant objects to their redshift. Hubble volume was calculated for the first time in 1929 when iconic astronomer Edwin Hubble discovered that distant galaxies appeared to be moving away from us at a rate proportional to the redshift of their light. He derived the Hubble volume by dividing the speed of light by the Hubble parameter. This spherical bubble encloses a region in which all objects move away from a central observer slower than the speed of light. All objects outside the Hubble volume in turn move away from the center faster than the speed of light. You may ask how it is possible for objects to move away faster than the speed of light. Well, that is possible, but that is where the magic of relativity comes in. There is special relativity and there is general relativity. What makes it possible for objects to move away faster than the speed of light is the difference between them. Speaking of special relativity, there is what scientists call an inertial reference frame, or to use a general term, a backdrop. The speed of light is constant in all inertial reference frames according to this theory. The speed of light remains constant whether, say, an observer is sitting still on a park bench on Earth or zipping past Neptune in an imaginary high-velocity rocket ship. A photon will always escape from an observer at 300 million meters per second and can never be caught up with. On the other hand, general relativity applies to the fabric of space-time itself. There is no inertial reference frame required in this theory. Because space-time is not expanding with respect to anything outside of itself, the speed of light does not apply as a limit on its velocity. So it is true that galaxies beyond our Hubble sphere are receding faster than the speed of light from us, but those galaxies are not exceeding any cosmic speed limits. Nothing violates special relativity to an observer within one of those galaxies. The space between us and those galaxies is rapidly expanding and stretching exponentially. Now, the implication of the Hubble volume and the expansion of the universe is that there are regions of the cosmos that we will never see. This is because even if we are patient enough, the light from these regions outside the Hubble volume will never reach us. There is a but though, because you might ask, what about the regions just beyond the reach of our current Hubble volume? Will we ever be able to see those boundary objects if that sphere is also expanding? Researchers say this depends on whether the Hubble volume or parts of the universe just outside of it is expanding faster. And the answer is determined by two factors. One, whether the Hubble parameter is increasing or decreasing, and two, whether the universe is speeding up or slowing down. Number 2, dark flow theory. This theory is born out of the fact that scientists discovered that there is an external force pulling on objects in the universe, implying there must be something outside the universe exerting the force. But how did we get here? Let's dig in. Dark flow is a relatively recent phenomenon as it began after the turn of the century. The density of galaxies within the universe is the same in all directions when viewed on a sufficiently large scale. Of course, this does not apply to smaller scale observations, as clumps of galaxies known as clusters are known to exist. Sir Isaac Newton actually proposed something similar to this concept in 1687. It was later proven by observation in the 20th century. When you think about it, everything is likely to be quite uniform if everything originated from a single point in the Big Bang and then expanded to form the universe we know today. There is something colorfully named end of greatness. It is no sad or unfortunate term, it is simply the distance one must travel out into the universe to find this apparent uniform distribution of matter. If you are thinking of jumping into your spaceship and heading to this place, it is about 300 million light-years away. However, things began to change in 1973 when a cosmological anomaly was discovered. This phenomenon also got an interesting name, the Great Attractor. This massive concentration of mass was calculated to be 250 million light-years away near the constellations Hydra and Centaurus. It has the mass of tens of thousands of Milky Way-sized galaxies. Its gravitational force is powerful enough to affect other galaxies and galaxy clusters over a few hundred light-years. However, the movement of some massive galaxy clusters that were thought to be affected by the Great Attractor was discovered to be racing towards a slightly different area of space, and this time scientists could not pinpoint a reason or cause for their motion. And according to Hubble's law, all galaxies should be moving away from each other in a uniform manner, preserving the cosmological principle. Then there was this 2008 discovery that changed everything. During a 3-year survey, the Wilkinson Microwave Anisotropy Probe, or WMAP, discovered a large group of clusters that all appeared to be moving in approximately the same direction at speeds of up to 600 miles per second. They were all aiming for a small patch of sky between the constellations Centaurus and Vela. Since they could not find a reason for this, scientists called the phenomenon dark flow. The effect of dark flow is experienced by different areas, which scientists arranged into overlapping groups using color codes. There is the blue sector, which includes the Coma Galaxy Cluster, otherwise known as Abell 1656. Coma contains over 1,000 identified galaxies. There is also the green sector containing a galaxy cluster designated Abell 667. There is also the yellow sector, which is special for containing the most massive object in the universe, the galaxy cluster Abell 1689. In fact, due to it having so much mass, its gravitational effect distorts the space around it to the point where neighboring objects appear bent out of shape, a phenomenon known as gravitational lensing, usually associated with black holes. Finally, the red sector is the furthest out, containing the strange cluster Abell 520. It has been dubbed the Trainwreck Cluster due to the chaotic nature of its internal structure. It is unusual because its dark matter content behaves completely differently than that of other clusters, and scientists have no idea why. The object outside the observable universe exerting this force has been estimated to be at least 46.5 billion light-years away. But what is this object exactly? We need to know because it can give us an idea of what lies outside the observable universe. There have been several theories. Could it be a black hole? If this massive number of galaxy clusters is being drawn towards a massive black hole, it would be accelerating. The dark flow, however, maintains a constant velocity over billions of light years, so a black hole is struck out. So the black hole concept, no matter how convenient it is within our knowledge, cannot thus be considered. Could it be a massive unknown structure? Well, that is not unlikely. Just because there aren't any massive structures with enough gravitational pull to cause the phenomenon within our observable universe doesn't mean they can't exist outside of it. The actual universe could be billions and billions of times larger than our observable bit, containing all sorts of things about which we know nothing. But there is another possibility. Could it be another universe pulling on these galaxy clusters? Number 3. Infinite bubbles. Researchers have tried to use the theory of the quantum foam, which we prefer to call the infinite bubbles theory, to explain how the cosmos is structured. And it could prove there are numerous universes out there apart from our own, which will show us what is out there outside the observable universe. Let's go back to Einstein's theory of general relativity. The issue is that his proposal only worked in smaller regions of space-time. When Einstein applied it to the entire universe, the predictions failed to match. To take care of this problem, Einstein proposed the cosmological constant, a fixed value that you can call a kind of anti-gravity, anti-mass, and anti-energy that counteracts the effects of gravity. Fast forward to when scientists discovered that the universe was expanding instead of static as Einstein had predicted. The cosmological constant had to be reset to 0 and largely ignored. However, scientists could no longer conveniently dismiss Einstein's anti-gravity suggestion after discovering that the universe's expansion is accelerating. To explain observations of the universe's ever-quickening expansion, what was previously assumed to be empty space in the universe had to be filled with massive amounts of mysterious anti-energy. Observations of the universe's expansion, on the other hand, indicate that the energy is 60 to 120 orders of magnitude lower than what recent quantum field theory predicts. This means that all of this extra energy is either effectively hidden or very different in nature from the energy we do know about when we look at the universe as a whole. Theoretical physicists attempt to resolve these mysteries by investigating the structure of so-called space-time in the universe at the smallest possible scale, and the results have been surprising. Space-time may not be the trampoline-like plane scientists once imagined. It may be a foamy mess of bubbles, each containing mini-universes living and dying within our own. What then is this space-time foam? This is where we say the universe may actually be full of bubbles. Physicist John Wheeler proposed that at the quantum level, space-time is foamy, containing constantly changing tiny bubbles. Recent research suggests that space-time bubbles are essentially mini-universes that form briefly inside our own. The space-time foam proposal fits well with the quantum world's inherent uncertainty and indeterminism. Space-time foam extends quantum uncertainty in particle position and momentum to the very fabric of the universe, so its geometry is not stable, consistent, or fixed at a tiny scale. To understand the space foam theory, imagine you are flying a plane over an ocean. The ocean appears smooth from high up there, but as you descend, you will notice the ocean is becoming rougher. You can see bubbles and foam near the ocean's surface. Similarly, space-time appears smooth on large scales, but rough and foamy on sufficiently small scales. The closer you get, the more complex an object becomes, which is just about what our universe appears like. The idea is that in space-time foam, every point in space-time has a massive amount of vacuum energy, predicted by quantum theory, but behaves differently than other points. For any particular way a point in space-time behaves, the inverse is equally likely to occur at another point in space-time. This is a property of space-time foam that kind of cancels out extra energy and expansions at a microscopic scale, resulting in the lower energy observable at the cosmic scale. Space-time foam is a complicated microscopic structure. You can think of it as an expanding universe consisting of tiny expanding and contracting universes at every point in space-time. Over time, the expanding areas of space-time will each replicate the complex structure and will be filled with tiny universes at every point. In that sense, every point in space-time becomes a microcyclic universe, revolving indefinitely from singularity to Big Bang to collapse. These bubbles have their own timeline because they are their own universes, and time does not have to function in the same way inside these bubbles because for the purposes of this theory and due to a concept known as entropy, the direction of time is not required to explain the quantum world. You might experience time backwards, sideways, or not at all if you were a subatomic piece of dark matter trapped in a space-time foam bubble. Dark energy would have to operate independently of our classical thermodynamic model while accepting the parts of it that we consider immutable. Number 4. Black holes. Here things get a bit biological as we're basically applying the law of natural selection to the cosmos. Fecund universes, also known as fertile universes, is a multiverse theory proposed by American theoretical physicist Lee Smolin. You can also call it the cosmological natural selection theory or CNS theory. The theory advances a process analogous to natural biological selection but at a cosmic scale. Smolin says the emergence of a new universe on the other side of a collapsing black hole causes the fundamental constant parameters, such as speed of light, Planck length, and so forth, to differ slightly from those of the universe where the black hole collapsed. As a result, each universe generates as many new universes as it makes black holes, so you have a black hole to thank for everything around you today. Thus, the theory incorporates evolutionary concepts such as universe reproduction and mutation, but it lacks a direct analog of natural selection. However, given any universe that can produce black holes that successfully spawn new universes, some of those universes may reach heat death with unsuccessful parameters. This is to say, fecundity cosmological natural selection says universes can die before reproducing successfully, just as any biological being can die without having offspring. Think of it this way. Assume we begin with 2 universes, one that produces 4 universes and the other that produces 12. These universes would reproduce and pass on some of their genes. The very fertile universes would then produce many fertile children, who would in turn produce many fertile children, and so on, until the vast majority of universes were very fertile. To put it another way, think of an alternate reality where the world contains stupid people that have far more children than smart people, and stupid people have stupid children. Given this, the Earth will soon be populated by stupid people. Many scientists have praised this theory and wondered why it has not generated much attention. This is because it can explain several aspects of our universe, including why the fundamental constants of physics are very conducive to life. For what it is worth, universes with large amounts of matter are more likely to spawn black holes, or, to put it another way, universes with the stuff of life stand a higher chance of reproducing than those without. In a way, this is essentially the multiverse theory on crack, or rather the landscape multiverse, which is the traditionally proposed model for the multiverse. These universal offspring would emerge from black holes, and genetic mutations would allow different physical constants to accompany the new baby universe. Furthermore, information cannot travel across the event horizon of a black hole, thereby creating a universe that is isolated and inaccessible to the parent universe. What this means is that we may never be able to see or interact with these universes. But at any rate, this theory indicates that outside our universe, there are black holes or more universes. It also means that there are probably universes out there that have similar characteristics to our own, meaning they may be able to sustain life in some little corner. The beauty of the fecund universes theory is that it can be subjected to scientific testing, unlike some other theories. For instance, if the theory is true, one would expect our universe to be tuned for black hole formation. Number 5. The theory of infinite parallel universes. Let's face it, parallel universes are no longer just a plot device in a good science fiction novel. Some scientific theories now support the concept of parallel universes beyond our own. But we agree the multiverse theory remains one of science's most contentious theories. Our universe is unfathomably vast. Hundreds of billions or even trillions of galaxies spin through space, each with billions or trillions of stars. Some researchers working on universe models believe that the universe's diameter could be 7 billion light years. Others think it may be infinite. So what exactly is the truth? Let's start from the beginning. Everything we know, including the universe, was an infinitesimal singularity about 13.7 billion years ago. Then, as the Big Bang Theory has it, the singularity exploded, expanding faster than the speed of light in all directions for a fraction of a second. The universe had exploded outward to 10 raised to the power of 26 times its original size in cosmic inflation in less than 10 raised to the power of minus 32 seconds. All of these explosions occurred before the actual expansion of matter known as the Big Bang, which was caused by all of this inflation. As inflation slowed, a flood of matter and radiation appeared, resulting in the classic Big Bang fireball and the formation of the atoms, molecules, stars, and galaxies that populate the vastness of space. Some researchers believe that the mysterious processes of inflation and the Big Bang show that multiple universes are possible, if not very likely. According to Tufts University's theoretical physicist Alexander Vilenkin, inflation did not end everywhere at the same time. It might have ended for everything we can detect from our location on Earth more than 13.8 billion years ago, but the process is still ongoing in other parts of the universe. This is referred to as the theory of eternal inflation, and when inflation reaches a certain point, a new bubble universe emerges. Those bubble universes are unable to communicate with one another because they continue to expand indefinitely. So even if we try, we could never get to the edge of our bubble where it might collide with the next bubble universe over, because the edge is zipping away from us faster than the speed of light and faster than we could ever travel. However, suppose we could reach the next bubble. Well, eternal inflation combined with string theory suggests that our familiar universe, with its physical constants and habitable conditions, could be completely different from the hypothetical bubble universe next to ours. In fact, this picture of the universe, or multiverse as it is known, explains the long-standing mystery of why nature's constants appear to be fine-tuned for the emergence of life. This is due to the fact that intelligent observers exist only in very few bubbles where the constants happen to be just right for life to evolve by chance. So the rest of the multiverse is still empty, but of course, there is no one there to complain. According to this explanation, it is possible that other intelligent observers exist in some of the infinite bubble universes beyond our own, but then, with each passing second, we move further away from them and we will never meet. However, one of the drawbacks of this theory is that the many worlds concept is not truly falsifiable, unlike the fecund universe theory. Some physicists support a simplified model of multiple universes. That is, if the universe we live in continues indefinitely, the building blocks of matter can only arrange themselves in so many different ways as they assemble across infinite space. Any finite number of particle types must eventually repeat a specific arrangement. In a large enough space, those particles must theoretically repeat arrangements as large as entire solar systems and galaxies. What this means is that your entire life, including details like what you had for breakfast yesterday, could be replicated elsewhere in the universe. So according to this theory, outside of our own universe, there are multitudes of other universes, and there is a chance that in one of them, there is another you living a similar life. Number 6. What is the universe expanding into? Most scientists agree that the universe is expanding, but that raises the question, what is the universe expanding into? We're used to this concept from almost all of our experiences. As an expanding balloon expands, as the air inside it expands, and the balloon pushes out against the molecules on the outside. But let us consider this for a moment. Do you really need the air to expand the balloon? Couldn't you, for example, simply take the stretchy fabric of the balloon and pull it in multiple directions at once, perhaps with 2 hands, perhaps with 4? In this case, the balloon's fabric will continue to expand. This is to show that there are plenty of reasons why something will stretch or expand. Now that this is established, imagine you're a tiny particle that can only live on and see a tiny region of this balloon. Supposing you look at any other part of the balloon, you'll be able to tell it's expanding because the things inside it will be moving away from you. Not only that, but the further away something is, the faster it appears to be moving away from you, as scientists have observed. But what is causing the expansion? Is it because the balloon's two-dimensional surface is being stretched by an unknown outside force? Is it because the two-dimensional surface exists in a higher dimensional space and something is blowing it up? Is there something inherent in the balloon that causes it to expand on its own? Or was there an initial set of conditions that the balloon's fabric began with that determined these expansion properties before anyone ever came along to observe it? The honest and uncomplicated answer is that you, as the tiny particle, don't know, and you can't know. You only see the balloon expanding from your vantage point. You can even assume that there is more balloon out there than what you can see. You can track exactly how the balloon is expanding today and how it has expanded throughout the history of the universe. You can measure the properties of everything observable to you and study how it affects and is affected by the balloon, and so much more. But you simply don't know what lies beyond the part of the balloon that you can't see, including dimensions beyond the two that make up the surface of the balloon. Our universe is a three-dimensional version of the balloon's surface, with galaxies baking in a massive loaf of bread. The bread represents the invisible fabric of space, and the raisins represent the galaxies within. We can measure the raisins within our view, which we define by the speed of light and the amount of time since the Big Bang, and assume that there are more raisins in bread outside of what we can see, but that's all we can know. We can ascertain the expansion history of our universe. We can discover that the expansion is accelerating rather than any of the other choices, and therefore define the expansion, but ultimately, we have more questions than answers about what's going on outside of what we can perceive. The fact is that the universe does not have to be expanding into something larger than itself. It could simply be expanding because that is what space does in general relativity. Let's hear what you think about what lies outside the observable universe in the comments section below.